Okay, in this activity, it was just an example of how to combine relative age dating and absolute age dating. So if you're watching this, you want to make sure that you've gone through both of those in the PowerPoint so you can kind of get an understanding. And this is how we combine them together. So in class, we would do this activity where I would have these little Legos. They were colored, and basically would give out a handful to different groups of students. And there'd be 4 different scenarios. And in this particular one right here, you would receive 15 blue and 15 red, where the blue Legos represent atoms of the parent and the red represents atoms of the daughter. And then say, okay, what can you do with this information? This would be information you would receive from, let's say, a lab. You send in your igneous rock sample, and it gave you some data. It counted the isotopes that were in this sample, the radioactive atoms, which are the parent, and the stable atoms, which are the daughter. So, of course, when you do a sample like that, you're getting millions and millions of counts, but of course, it's hard to manipulate those numbers in a classroom, so we do some basic stuff like these numbers. They still work, and the idea is that what do? You're like, okay, I don't know what step to take here. So the first step always is to remember that the main rule of absolute age dating is you cannot have any daughter atoms in the initial igneous rock when it cooled and crystallized. We know that by knowing the chemistry of the igneous rocks and how it formed and, field observations, all this kind of stuff. But if that's true, then we know where to start, because all of these atoms that are now daughter must have once been parent, because this has to be 0. And so what we could say is, I've got this from my starting point, right? The parent, I'm just going to add the 15 together. So I have 30 atoms of the parent, and for the daughter, I have 0, right? So that's my starting point. So then the idea is how half-lives are going to work, and this is super basic, of course, but the idea is that we take half of what we start with, and that would be the time it took for that material to decay. And so half of 30 is 15, and so my new value for my parent would be 15, and those have all been converted to daughter. And so I have this ratio after 1 half-life. And that's what I see today, suggesting that that's what's happened, 1 half-life. So that's what we would write here, say, look, there's just been 1 half-life. And if the system is saying that it takes 120 million years for 1 half-life, then A has to be 120 million years old. That's simple. And then we can use that to interpret our cross-section here. So we could make some observations here. These are all sedimentary rocks except for A. There is a baked zone on the bottom. This suggests that this molten material was deposited here and there was nothing above it, because if layer B was there, it would have this squeeze between there and bake it. Because it didn't, it suggests B didn't exist. So we would interpret this as a lava flow. So the order would be E, then D, then a lava flow, then it cooled and crystallized, then we added B and C. So that's the order, right? Oldest is E, youngest is C. But what else could we do? Well, we can reference this 120 million years and say, well, look, these 2 layers here must be older than 120 because they're below it. And these 2 layers must be younger than 120. Is that amazing? Well, no, but it's better than we had, because this whole sequence could have happened 1.2 billion years ago. I don't know that, but now at least I have some idea of what's going on here. And of course, I could use other things to help me narrow down age, like fossils and things like that. And so that's just the game you play. Now, it's not always just one, but the process is always the same. If we look at this example here, now remember, we have this granite. That is an igneous rock, but there is no baked zone where it is in contact with the sandstone, which means it didn't intrude into existing rock. It wasn't molten and came in and touched B, because if it did, it would have baked it. When there's no bake zone, it suggests that the granite was uplifted to the surface and weathered away. And that was the surface of the earth. The granite was exposed there. And then I deposited sand on top of that. And then the other layers, they were buried, and then they were turned into rock layers. And so the order here, based on our relative, is we have the granite first, then we have B, E, A, and this cuts across it. Must be the youngest thing here. But how old is A? Well, we can do the same idea. Remember, we always said that we have to start with 0 daughters. So I'm going to take those 30 daughters and add them to the 2. So my parent's starting point is 32, and my daughter's starting point is always 0. But that is not what I have here when I got that information back from the lab. So I want to take half-lives until I get to what I have. So of course, if we take half of 32, we get 16. And where did those 16 go? Well, they turn into daughters. So this is the ratio after 1 half-life. So it took 50 million years, because that's the half-life for the system, to get this ratio. But that's not what I have, so I want to just keep going. So we say, what's half of 16? We get 8. We add those 8 to the 16. We get 24. That's not what I have. I got to keep going. And so I take half of 8, I get 4. I add that to the 24, I get 28. Holy crap, I take another half, and I get 2, and I add that here, and I get 30. And we're like, yay, that's what we have. But how many times did I take half? So don't just count the numbers, because that's not how many half-lives. I went from 0 to 16, that's 1. 16 to 24, 2. 24 to 28, 3. 28 to 30, 4. So there were 4 half-lives in this scenario. And then, of course, it took 50 million for each one. So 4 times 50, this is a 200 million year old rock. Now, how does that help me? Well, same thing. It tells me, of course, that the age of some of these things. But if I have some additional information, like in this layer here, there might be some fossils or some other evidence that allows me to get an age on this layer. If this is 250 and this is 200, it kind of brackets layer C. So layer C has to be younger than 250, but this is 200, so it has to be, that's which saying it existed when this came through. So this is also older than 200. So it's between 200 million years old and 250 million years old, right? And so that can be useful for us figuring out something that happened in layer C, and we know a time period. At least we can bracket it down. Okay? And of course, we can just keep going and playing that game. Same thing here. Look, different half-life, but look, the values are still, this is how we figure it out. All of the daughter, has to have started out as parent. So we're just going to add those together. So the parent starts with 40. The daughter always starts with 0. And then we just take half. And so half of 40 is 20, and half of 20 is 10. And that's how many parent I had. And so it just took me 2 half-lives. So we only had 2 half-lives here. And of course, we could say that then that mean this is 1,400 MA, or we could say it's 1.4 GA, which stands for billion. And so, same thing. What does that tell us? Well, look, we know something about the order based on our knowledge of relative. We have the age of this. D and E, they were there first. And because this bakes top and bottom, it suggests that B existed before this came in, because it oozed in between these 2 layers and baked both of them. And so what does that tell me? Well, B, D, and E have to be older than 1,400 million. Okay. Now C, unfortunately, I don't know what's going on there because there's no interaction there. It could either be as old as these, all 4 could have been there and then this oozed in, or just the 3 oozed in and this came later. So we have to be aware of some of the limitations that our numeric values can give us. And then finally, we could go to this last one, and hopefully by now you get the procedure. You're just going to say, okay, parent, I got to add them back together. I'm back to that number 40, and my daughter product is always 0. And now I'm just going to go halfsies, right? Half of 40 is 20, half of 20 is 10, half of 10 is 5, and boom, I went 1, 2, 3 half-lives. So 3 half-lives here, We multiply this by that, we get 900 million. We'll do MA, right, for that. So what does that tell us? Well, without that information, let's think about this. So I have layer E, D, C, B. Now, this layer here does bake these layers, suggesting, right, that it did intrude, not like the previous one where it was already exposed at the surface. This intruded into existing layers. Which ones? Well, E, D, and C. So those all had to be there before this could ooze in. So we know that these are older than 200 million because we have this. But our layer up here bakes layer B, and it says that this is 900 million years old. So now what does that tell us? Well, even though there's no relationship to Z and B, I know that E, D, C, and B all had to exist before A got here. And A is 900 million, so these are all 900 million years old. And so it's E, D, C, B, a big lava flow. And then 700 million years later, this thing came along and intruded into here. And because I know A, I can tell you that story. If I didn't know, it would be hard to know when A arrived. It could have been after or before, we wouldn't know. So this is how we combine these kind of two techniques, relative age and absolute age. And of course, that helps us narrow down, an interpretation, helps us tell a better story. The more data, the better always. All right, so that's kind of the activity we would perform in class. And once people got the first starting point where, you always have zero daughter, they usually can get through it. And hopefully this makes sense to you. All right, so hopefully that was helpful. And if you have questions, of course, don't hesitate to contact me.